Hi. Okay, I wanted to address a problem that I put out on LinkedIn about eddy currents, and it's a problem that's kind of been on my mind for the past 15 years as a sort of a thing that you see and you don't know the reason. I put it out, and I always kind of raise it whenever we're having discussions about eddy currents to see if anyone has a decent answer. And I never had the time or the energy to really sit down and think about it myself. So I put it to Ed Korkowski on LinkedIn, and he was very generous to make a video explaining, the problem. And the problem is when you get a defect at two standard depths of penetration, why does that show a reduction in inductive reactance? Okay, so a defect at two standard depths of penetration was shown on your screen at 228 degrees. That's what they always say. But on the impedance plane, that would show that the dot is moving south, a reduction in inductive reactance. So if you have a defect at one standard depth penetration, which is shown on your screen at 114 degrees, or if you're using F90, a frequency that puts it at 90 degrees to your liftoff line, that's going to be showing an increase in inductive reactance. So why does a defect at two standard depths of penetration show a decrease in inductive reactance? Intuition would say that any defect disrupts the eddy currents. The eddy current's secondary magnetic field will be compromised, and the primary field in the coil will generate more inductive reactance. So I started thinking about this, and I might have a theory, but I'm not a physicist. I don't work for Z-Tech or Edify. I'm not as clever as those guys, but I think I might have a theory for it. So when you have a test coil, you have a primary current that is being driven by the voltage from the amplifier. And when the current starts moving, it creates a primary magnetic field. And because we have this test coil, we have an inductor. The lines of the flux of the primary magnetic field, as they cross through the loops of the coil, they set up an electromotive force, a force that is in opposition to what the current wants to do. So you can imagine a current in a sine wave, and the first quarter of that sine wave, the first 90 degrees, is trying to accelerate. The current is trying to accelerate in a particular direction. Let's call that clockwise. In a clockwise direction. And this primary magnetic field sets up a force in the opposite direction. It's a bit like if you were trying to jog down a street or run down a street and you were trying to accelerate, and there's a headwind, resisting your acceleration in that direction down the street. And then when it collapses, it does the same thing. You're trying to decelerate, and there's a tailwind keeping you pushing along. So it's always trying to do what the current doesn't want to do. And if you have your test coil in air, and I'm talking about a high frequency surface coil for aircraft inspection, I don't know about you pipe and tube guys, how your coils work, but the same principles, I'm sure. So if you put your test coil up in the air, your high frequency scratch test coil, that's what happens. The primary field is allowed to expand out. It creates a lot of electromotive force within the test coil, which is called inductive reactance. And it causes the current to lag behind what the voltage is trying to do. When you put it down on the surface of the part, you create eddy currents. And the eddy currents at the top will be pretty instantaneously created. And the field, the secondary field that the eddy currents produce, will be expanding and collapsing in sync with the primary magnetic field, pretty much. So these are in phase. And this secondary field, the purple one here, it interacts with the test coil as well. But because the eddy currents are in an opposite polarity to the primary current, and therefore the field, the secondary field, is in an opposite polarity to the primary field, the effect that it has on the test coil, it does induce an electromotive force, but it's the opposite effect of what the inductive reactance is. It's the opposite to the electromotive force that the primary field is producing. So the primary field is inducing inductive reactance within the test coil. The secondary field is inducing the opposite, which we can call capacitive reactance. There isn't a capacitor here, but it's the opposite to inductive reactance. And it cancels out a lot of the inductive reactance, because you can imagine as you're jogging down that street, you've got a headwind working against you. That's the primary field doing that. The secondary field is giving you a tailwind. So it kind of cancels the two out. So the net sum of the reactances almost cancels out, not completely, but it does cancel out a lot of that inductive reactance. So if we go to a diagram like this, so this is your impedance plane. Just take a look at the y-axis here. Sometimes you'll see these pictures labeled up as XL, sometimes XL minus XC. So the net result, the net sum of the two reactances. Sometimes you'll see it as delta X, X being the net sum of the two reactances, one subtracted from the other. Delta being the net reactance from your measured instantaneous position, wherever the coil is, minus X reference, which is where you nulled or balanced. Whatever. It doesn't matter. For the purposes of what we're going to talk about, we will just say that this represents increasing inductive reactance. Okay. If it's delta X, it's the same deal. As far as I can tell, it's the same deal. If you have an increase in inductive reactance, the dot will move north. Okay, so we'll just call it XL. Same down here, this will be delta R, but we're not going to about that. And yes, there's normalization, there's scaling, there's offset subtraction to move the air point hard up against the y-axis. But we'll keep it simple. So this is your air point. And so when you drop it down into your test surface, you get a large cancellation of that inductive reactance, because that secondary field is creating capacitive reactance effectively in the test course. You get a large reduction and your dot moves down like this. You get a large reduction in XL. So if you imagine that this is your liftoff line or something similar, and you can draw a test screen like this. Okay, so this is the top of your screen here. So you've rotated it using your angle control. This is your liftoff line coming up here. And so a defect will do something like this, like a defect of one standard depth of penetration. It'll do that. So you'll see that it is increasing in inductive reactance, yes. The dot is moving generally in a northwards position. And that's right, because if there's a defect of the surface or near the surface, that's going to disrupt those eddy currents, producing that capacitive reactance. And you're going to get more inductive reactance as a result, a net result. So this is fine. So the question still remains, when you're at 2 standard depths of penetration, that's shown as a 228-degree rotation. And so the defect would do this. So why? Why is inductive reactance decreasing? Okay. So I have created a really terrible animation to try and demonstrate this. So here's your primary field. It creates eddy current to get the secondary field. There is time lag between the primary field expanding into the component and creating these eddy currents. So here's your first pool. Here's your second pool. The primary field, you can see, is still increasing. So is the secondary field of the first pool of eddy currents. And now we're hitting the second pool of eddy currents, so the orange field. Okay. Now the primary field is at maximum strength. And we're just starting to create eddy currents down here with the blue field. Okay. Now the primary field, the red one, is starting to collapse, but the secondary field of the eddy currents down at the bottom is still increasing. Now the primary field has done 180 degrees of its sine wave, and it's coming to a collapsed position. And the secondary field of the eddy currents down at this position are now reaching their maximum. So there's a lag, and now they're collapsing. Okay. So it's a pretty bad animation, I understand, but I'm not a VFX artist. So there's lag, okay? But the field still interacts with the test coil at this depth. At its maximum position, it does interact with that test coil. So just drew some graphs. So if we create another one of these. And let's take out that black line. So a real professional would have done this previously. That's fine. Okay, so you can imagine that this is the primary current in our test coil, okay? And this is the act of the electromotive force from the secondary field. Now we'll start with the eddy current at the top of the component, the surface eddy currents, and the secondary field, and what it's doing on the current. And that is, like I said, it's largely in phase with the current of the test coil. So orange is the current in the test coil wanting to accelerate in the clockwise direction. So you can imagine this side of the sine wave, this is clockwise, and this is counterclockwise. So in the clockwise direction, the current in the test coil is accelerating, and then it doesn't want to travel in that direction. So blue represents it doesn't want to travel clockwise, it wants to travel counterclockwise. Now it is traveling counterclockwise. Now it's decelerating, it doesn't want to travel counterclockwise, it wants to travel clockwise, and so on and so forth. So the secondary field of the eddy currents at the surface is in phase. It's happening pretty much at the same time, and it is helping the current do what it wants to do. Like I said, the primary field of the test coil is producing inductive reactance. It's stopping the current in doing what it wants to do, whether it's accelerating or decelerating in whichever direction. The secondary field is adding capacitive reactance, and it's helping. So this electromotive force is matched. Okay, it's helping the current in the test coil do what it wants to do. Okay, and the effect is capacitive in totality through that sine wave. But as you go deeper and deeper, those eddy currents are being created later and later. And the effect that the secondary field of those eddy currents have on the test coil is going to be lagged and lagged and lagged. So we'll put this diagram of the electromotive force down here. Let's put it at 114 degrees, let's say. So we're talking about that 2 standard depth penetration defect. So you can see I've moved it 90 degrees, okay, and we'll do a little bit more. So we'll call that 114, okay. And so what's going on here? And I'll just take a little bit more just so I have a bit more of that one. Okay, and you can pretty much ignore this. Okay. So what's going on here? We'll take it from this point. You can see that this we have blue versus orange, basically. That's not good. That's in opposition, and that is an inductive effect. It's an inductive reactance. It's not doing what the test coil wants to do. It's not helping the current in the test coil. So you've got blue versus orange all the way here to here, okay? So this is an inductive effect happening here. Then we've got blue on blue in this region here. Then we've got blue on orange, and you can imagine that goes into more orange here. Let's take a bit of that. Up there. Okay. And then we've got orange and orange. Put about there. Okay. So you can see where they're not matched up. This is an inductive effect. Got blue and orange. Where they are matched up, that's going to be a capacitive effect. And you can see it's mainly red. So the effect that the secondary field at that depth is having on the test coil is mainly the net result is inductive reactance. It's adding a little bit of capacitive reactance. When you look at instantaneous positions across this sine wave, some of it is capacitive effect, the green, but most of it is an inductive effect. And so when you remove that, when you remove this secondary field or disrupt it by adding a defect at 2 standard depths of penetration, what you're removing is a mainly inductive effect. And so on your test screen, you will see a reduction in inductive reactance. So if we take a look at that again, like I said, the secondary field at the surface is mainly in phase, and that's all going to be a capacitive effect. Okay, so it's counteracting that inductive reactance within the coil. As you go deeper, the effect of the eddy current secondary magnetic field on that test coil is shifting out of phase, and it's going to get more and more and more inductive. If you have it like this, 180 degrees out of phase, you can see that's a completely inductive effect. Everything's mismatched. Okay, so 180 degrees, well, that's actually just below 3 standard depths of penetration. So between that point and the surface, you're going to have varying amounts of, here's total inductive reactance, here's total capacitive reactance. You're going to have varying amounts, right? So if you have a coil like this, at the top, it's mainly XC. Okay, and at the bottom, it flips to an inductive effect. But these eddy currents down here, and this is the best way to think about eddy currents, is that it's not, sometimes it's drawn as like a whirlpool. They're not. It's better to think of them as a cylinder. They're drawn as a whirlpool just to show you that they're diminishing in amplitude or strength, but they're not changing in shape. Okay, well, they might even spread out laterally as they go deeper, to be honest. So think of it as a cylinder that's getting weaker as it goes down. So the effect at the top is mainly capacitive. The effect as you go deeper is flips to inductive. And that's right. So you can see that near the top, yes, you'll get a decrease in inductive reactance, sorry, an increase in inductive reactance. And as you go deeper, the defect will start to do this. A defect may give you a sideways motion, basically neither an increase or a decrease in inductive reactance. Yes, that will be somewhere in here. Okay. And at a certain point, it flips so that the effect that you're removing is an inductive effect, and you're getting a reduction in inductive reactance by putting a defect down there. And then, finally to 3 standard depths of penetration. And Ed Korkowski was perfectly right when he said, well, you shouldn't even be looking at for defects at 2 standard depths of penetration. Perfectly right. You're never going to see a defect at 2 standard depths of penetration in reality, because on your test screen, here's your liftoff. You're looking for a defect like this. As a defect at 2 standard depths of penetration is going to be like this. It's going to be so small. You're just going to see that as like dot movement or like noise. You're not going to sit there and go, oh, that's a defect at 2 standard depths of penetration. And this is kind of a bugbear of mine. If you look at an aircraft manual of a very famous European aircraft manufacturer, and I think it's manual 516000, it even says in there the EDP, the effective depth of penetration, is 3 standard depths of penetration. And I think that's at best misleading, because there's no way you're practically effective down to 3 standard depths of penetration, because the amplitude is so small. So yes, when you hit a defect at 2 standard depths of penetration, there is a reduction in inductive reactance, because at that depth, the effect is mainly inductive. So by putting a defect there, you're removing that effect. And so you'll get a reduction. But it's still small, because the eddy currents down there are very, very weak. So yes, the dot moves south, but with not much amplitude, not much dot movement, because the eddy currents are very weak. Anyway, so that's how I've kind of logicked it out in my head. Like I said, I don't work for an eddy current company. I'm not a physicist. And if anyone out there wants to add to this, then I'd be more than welcome. Always willing to learn, etc., etc. So thanks very much.